In this chapter so far, we've looked at how we can use dimensional analysis and the Buckingham pi theorem to develop these relationships between pi groups, different pi groups. And now we're going to return to this idea of modeling and similitude to show how we can use those concepts. The example we talked about earlier in class was this idea of developing a scaled down version of an airplane wing. And let's say you take force measurements on that wing. Well, how do you know that those relate to the large scale original version as well? So that's what we're going to talk about today with this idea of modeling and similitude. So let's define some terms first. What do we mean when we say a model? So the technical definition of a model here is a representation of a physical system that may be used to predict the behavior of the system. Now, we usually think about models being smaller than the physical system that they represent, but they can also be larger. So in some cases, you may need to scale something up in order to do some studies about it and to learn about its behavior. So it may be smaller or larger than the actual thing. Now, the actual thing is known as the prototype. So the prototype is the actual thing that you are, with its actual size that you're trying to study, and the model is the scaled down or scaled up version that you build in order to do some studies on and to test. So for example, the example that we've talked about is a scaled down airplane wing in a wind tunnel. Right, we have to make these wings smaller to fit inside a reasonable sized wind tunnel, and so we scale that down. So the question that we come to then, if we make this smaller version or larger version of our prototype, so if we make a model of our prototype, how do we make sure that our model results will also describe the prototype or the original system? Right, we don't want to go willy-nilly and just assume something about the results that we get from our model. We want to make sure that we can actually faithfully relate those results to the large-scale version or back to the prototype. So how do we do this? So the answer here is that by making the independent dimensionless numbers that describe both systems if we make both of those the same, and this condition is known as similarity, by doing that, we can ensure that the dependent dimensionless numbers also will be the same. Now in class, we did an example looking at the pressure drop in a pipe. So, so from our previous example, so we were looking at the pressure drop per unit length. And we developed this relationship that delta P sub L, which is our pressure drop per unit length, times D, the diameter of the pipe, divided by rho V squared, so that's the density of the fluid times the velocity squared, is a function of rho VD over mu, the density times the velocity times the pipe diameter divided by the viscosity. And so this is our relationship between two dimensionless numbers. All right, the one on the left-hand side, this is our dependent one, and then the one on the right-hand side, this is our independent. And so we developed this relationship between the two. So in order for these to be similar, and this is using this technical definition of similar, the model system must be designed so that the Reynolds number, this is rho VD over mu, of the model, so rho of the model times V of the model times D diameter of the model divided by mu of the model is equal to rho VD over mu of the prototype. So just to be clear, this combination, all of these variables represent the model, and all the variables here represent the prototype, which is your original system. So in order to be similar, if we can design it so that the Reynolds number of the model is the same as the Reynolds number of the prototype, then what we'll find is that this delta P sub L of the model times D of the model divided by rho of the model times the velocity of the model squared is equal to delta P sub L times D over rho V squared of the prototype. So basically, if we can make sure that the independent dimensionless groups are the same for both our model and for our prototype, then that will ensure that the dependent variables or the dependent pi groups are the same as well. Now this is nice because what we can do here is we can solve this equation for delta P sub L. So we can actually solve this if we go and do a bunch of experiments with these parameters, then we can come back to this expression and we can solve for delta P sub L. And what we find here is that we have this series of ratios. So we have D of the model over D of the prototype times rho of the prototype divided by rho of the model times v of the prototype divided by v of the model squared times delta p sub L of the model. And so this is powerful because we can go and do all these experiments to find delta p sub L m, and then come back to this equation and calculate delta p sub L. So I'll make a note to that effect. If you measure delta p sub L m in the model system, you can calculate delta p sub L in the prototype, which is, again, your original system. So this is a very powerful technique. You can go do experiments with your model system here, which are smaller perhaps and easier to do. You find your results, you measure things like delta p sub L m, this guy right here, and then you can go back to this equation and plug things in, and you can find a result for your original system or your prototype. Now, one other note here is that in this example, we only had had one independent variable, right? Which we use to find the dependent variable. But that's not necessarily always true. Sometimes you have 2 or 3 or 4 or more independent variables, and so if that's the case, you have to enforce similarity for all of those variables. So we only had to enforce similarity on one pi term in this example, but in general, all pi terms must be similar. Now there are a few different types of similarity which we need to talk about. Similarity. The first type of similarity that we need to talk about is geometric. And so this refers just to the size and the shape and the dimensions of the model and the prototype. So this means that the model and prototype they must be the same shape and the dimensions must be scaled by a constant. So for example, we have a skyscraper here in Tampa Bay, or Tampa, downtown Tampa, that's sometimes called the beer can skyscraper. This skyscraper has a height of and a diameter of 62 feet. So perhaps we might want to do some wind tunnel testing of a model of this skyscraper to see what sort of vortices it's creating, what kind of aerodynamic forces are being generated. So we would need to make a scaled down version of this skyscraper. And so we might want to say we want to make a 1/500th scale model. And that would have a height of 0.91 feet and a diameter of 0.12 feet. So we're just dividing the height and the diameter by 500, and we can write that expression as this ratio. The length of the model divided by the length of the prototype is equal to 1 divided by 500. So you can apply that to both the length or the height and the diameter to find the appropriate dimensions of your model. So we're just dividing through the original by some factor, some constant factor, to get the dimensions of the scaled version, a geometrically similar scaled version. So that's the first type of similarity. That's a pretty common one that you have to enforce. Second type of similarity is kinematic similarity. And this refers to the velocities being in the same direction, but only differing by some constant scale factor. So here are the velocities at corresponding points. Are in the same direction. And they only differ by a constant scaled factor. So that's your kinematic similarity, referring to the motion and the velocities being the same. And the third kind of similarity, and sort of the most difficult to achieve, but also the most important in many circumstances, is dynamic similarity. And dynamic refers to forces. And so in dynamic similarity, we require that the flows around or in, if you're looking at an internal flow, the flows around or in the model and prototype have the same force directions and the magnitudes only differ by a constant scale factor. So those are the three kinds of similarities, and in general, you have to enforce all of them in a problem. Although sometimes it's not possible to enforce all of them, and so sometimes you have to pick and choose. Sometimes you can enforce dynamic similarity, but you might have to sacrifice some aspect of the geometric similarity. But those are the three kinds of similarities, and in the next video, we'll work an example.